Okay, all right. So I'd like to pick up where I left off before and expand things a little bit for the collection and kind of tell you what we're up against and kind of show you an example of how things work. So if you recall before, if you look at this, if you look at this set of rules, it's a little bit more detailed than what we had on the screen previously. This part remains the same, and what we're now doing is being very careful about all the collection stuff, so that looks like there's one more person to admit. Go. So essentially what we're doing is we're making sure that we follow the same procedures, that everything is very consistent. So you'll see that, for example, in the same way that this information is giving us this information is going to give us these rules. What's different though is that this is kind of already, so this is already at the level of types in some sense. They're already collections, and so they don't have the same witnesses. So this one clearly has a notion of a term as a witness to a type, and then a kind of an injection from type to a kind. So we will have a notion of types and injections, but the witnesses are going to be different. They're not wired in the same way. And then the other thing that we've done is to carefully create type rules that come from the tying the recursive knot. So if we go back here for a minute, so if you remember in our example, we build the type, L of P phi of X, and that's going to be that's a two-level type decomposition, but ultimately we're going to tie the recursive knot, right? So we'll get an R of this thing, which is going to close up the hole in the parameter, or one of the holes in the parameter. So we need to make sure that our type rules match that. And so that's what's going on in this section here. In particular, let's run this very carefully, right? So these are trees, right? So we've used this for the empty tree, and we've used this for adding something to a tree. So there's an operation like this to add something to a tree. So this says that you've got an empty tree. So this is a type variable that's ranging over types, and that is of that kind. So we're kind of up one level than we are with these productions, right? And then if you have that L is of type A and you have the M is of type list A, then you have that L plus M, so that's this thing, is of type A tree plus list T of A. Right, so that basically just reflects this. And then we need the corresponding injections, right, which is that if L is of type empty tree, then L is of type tree, and if L is of type A plus list A, which is this side of it, then that's of type, then that's of kind T of A. Right, so that's So these things reflect what's going on in this production. And then these correspond to tying the recursive knot. So in particular, we say that if X is of kind P, right? So X is now one of these types here, then X is of kind T of P. But also, if X is of kind T of P, then we get to conclude that X is of kind P, right? So this says that that P's are collections, right? So that's tying the recursive knot. And similarly for the N, right? And once we tie the recursive knot, then we know that these things end up being collections, right? That's what's happening here. So any questions about that before I look at an example?
You said L in the statements before the last one. You said L is of type empty tree.
Mm-hmm.
Did you mean L is the kind of empty tree? Or
yes, yeah. The reason
okay.
I'm saying that is is we want to keep in mind that there's terms are of types are so terms are of type right? Type is of type metatype, but a metatype is a kind, and then a kind is of type metakind, and so on, right? So there's this infinite hierarchy that we can go up. Any other questions about this?
So what is it that you mean when you say witness? Can you clarify that?
Yes, a witness is it's basically a form of proof, right? When you can produce a witness, you in the standard set theoretic version, we're saying that this occurs in this. Likewise with this tree thing, we're saying that this occurs in that. So this colon is occurs in, and this colon here. So this colon is occurs in, this colon is that there's an injection from here to here, right? So this is a co-product, so there's an injection from here to here. This is a co-product, so there's an injection from here to here, right? So that's why these rules exist. Like there's the injection, there's the injection. Does that make sense?
Yeah, it makes sense.
Can I just ask you about this recursive tying the knot? Can you maybe give us some simple example? This P equal TP. How?
Sure. I mean that's what row calculus does all the time, right? So like this is only the first instance of row, right? This isn't row yet. It only becomes row when we set X equal to N, right?
I see.
Right. So when we set X equal to N, well, and so you'll say that the R is equal to P of N of R, right? That will be the and that will tie the knot, right? That will make P's and N's depend on each other, right?
Oh, I see. And
that's what we're doing here, right?
And if you want to implement this, in some existing language, we will need to create some additional type so that we can use it for this tying the knot.
Yeah, that's right.
Because okay.
Yeah. Okay. So then these are the kinds of rules we can do. So for example, if M is of kind empty, then we get to conclude that M is of type TP, which means we can also conclude that M is of type T of TP. From here, we can conclude this. Notice that I've dropped the witness. So I've kind of done that for convenience, but we'll ultimately have to either carry the witness along or have a rule that allows us to drop witnesses and just consider this portion of the rule. Once I have these two, then I can obviously combine these, right? Because this is of type list and this is of type P, but P can be T is, we can get that, you know, so this is list of T of TP, this is TP, right? So we can do the add, right? This is A and T of A, right? So I can do the add, which allows me to get this, if I cons 0 onto list M, right? If I add this as the root of the tree, then this is that type. But now I can start collapsing this going the other way, right? So I collapse this, collapse this, collapse this. So I get this is of kind P. So that begins to show you that these things are in fact collections. That gives you an example of how to use these sorts of systems to prove things. Now, the important thing is that you know, it will often be the case that you have to give the proof system some guidance, or it'll start it'll, you know, like in this case, you can go around the loop, right? So you have to prevent this thing from cycling. So you have to give it some goals, some guidance with goals to keep it from cycling. Hopefully that makes sense, right? You see what I'm saying? Like you can run these rules in circles. And so, you know, if you just naively try to drive the proof system without some goal direction, it can sit around and run loops like this. So you have to keep it on the straight and narrow, so to speak. Which is why it's important to have both the model theoretic view as well as the proof theoretic view. So hopefully that also makes sense. Any questions about that?
What would be the goal, for example, to
Well, the goals are going to be, you know, I've got an actual type that some programmer has declared, and I've got an actual program that some programmer has written, and I really want to check that that assertion that the program is of that type is correct. And so I'm trying to get down to ground, like this is ground, and this is ground. So I'm trying to get down to ground, and if I notice that I've gone around the loop, you know, more than n times, then I need to stop that. I need to curtail that behavior.
Oh,
That-
I see.
Yeah.
So basically, we are like partially running some program, and we can think in situation where, yeah, I'll think about that.
Okay. I mean, it's fairly standard in systems like this to kind of drive them, right? Because, you know, if they are Turing complete, then, you know, it is quite possible to get lost in the proving. and so so you give them goals. It's spiritually, that's kind of how prologue works, right? It's like when you do your proof search, that's what the cut operator is doing, right? The cut operator is kind of pruning some of the proof search. So the goal directedness is to prune some of the proof search, so that, because there's some areas of searching the proofs that are not productive with respect to what programmers want the proofs to do.
Yeah. Maybe something like something like all the natural numbers, and we can say we can reduce the searching for all the numbers, right?
Yeah, exactly. That sort of thing. Yeah, exactly. Right. So that's all I had prepared for today. Any other questions, comments, or
So, like, when you're doing this proof search, like, you'll allow for things like recursion is a valid way to argue that something is a valid like type and so on.
yeah, of course. But notice that recursion in row is done explicitly, right?
Okay.
Recursion is really happening because you have these two operators dual to each other. So you can build recursion at the term level, right? Using the duplicate operator that I written up in the original row paper. So at the level of terms, I have the system does deal with recursion. So again, if you do type a recursive program, you're going to have to be careful about, not going too deep into that recursion. And this is very similar to what Kairos points out in his a spatial behavioral logic for the pi calculus, where he identifies that the type system is very strong, and because it's very strong, there's some typing judgments which will take forever. Again, he's looking at it from a model theoretic perspective rather than a proof theoretic perspective, and so he's not looking at it in terms of judgment rules. He's looking at it more the other way, that he's looking at it in terms of semantics that are similar to this. But it is the case that if you don't restrict the semantics and you don't restrict the programs, there are some model checking requests that will never terminate, and that's totally reasonable. It's totally okay. And then what he does is to identify a subclass of pi calculus programs for which you can tell that the model checker terminates, and B, they're interesting programs, right? They allow programmers to say a lot of things, and it's a very similar situation, say, with system F, right, where the type system for system F is the lambda calculus at the next level up, but for the lambda terms that are well typed will be terminating, right? So there, what we're saying is, so since they are terminating, it's obviously not, the well typed terms are not Turing complete. Right, so lambda is Turing complete, but the well typed terms under system F cannot be Turing complete because those terms are strongly normalizing. So the moral of the story is that you have two dials, two knobs that you can twist in systems like this, right? So we can take fragments of the term language, and we can put some extra constraints on the type, right? And with either one of those, we can pick out interesting fragments where you do get termination of the type check. So that's essentially the story with respect to recursion, both at the term level and the type level. And of course, you can also do the blockchain trick, right? You can add gas, right? So you say, you know, go and do the type check, but here's your budget. So if the type check costs more than this, I'll think of something else to do.
May I also ask you, with this hierarchy of types, like term, type, and is it going to be possible to is the type or kind will be first class and like available on the term level, so that
no. We haven't done any kind of dependent. We haven't done any reflection for types. We haven't said here's a way to turn a type into a term, nor have we said here's a way for terms to. We haven't done any dependent type stuff. So neither reflection nor dependent types is treated here.
Okay.
Yeah.
But you're not saying this is not direction that you want to go.
Yeah, I'm not saying it's not interesting. It's certainly interesting. It's just, you know, I'm trying to do one step at a time, right? I mean, these dependent type systems are all about variants of lambda, right? And what I'm trying to do is to widen it the other direction. I'm saying all of the, you know, I'm generating types for all rewrite systems of a certain kind, right? Which is, so I'm going wide that way, right? So you can think of, you know, things like system F and dependent types and other kinds of variations. They're all about deepening the type side, right? And what this is about is widening, deepening the type side in a certain way, but only so far, right? I've got clear bounds on how I do the types, and then widening the range of inputs that the type system algorithm accepts. That's really what OSLF is all about.
So I have another question, and it's actually a two-part question because we were discussing it in the Discord, right? It's close. So the first thing is that we're keeping track of the execution history and the blockchain, right? So I was asking like the other question, like this particular part of this particular subprogram, right, does not have race conditions. Then if you can prove it beforehand, and all validators know it, then you can reduce the amount of communication that you do between the different validators, right? So the first part is that how does execution history, like, because execution history is essentially a sequence of programs, right, which are like transforming from one to the next atomic steps.
It's
right?
yeah, you can think of it as a trace, right? But
Yeah.
But if it is a trace, right, notice that trace equivalence is not sufficient to guarantee equivalence of programs. Right? So you just have one trace, but that doesn't necessarily.
Yeah, exactly. So if I have to prove a theorem, what is the general framework to ask a question like this program will never have any race conditions, right?
Yeah,
So then
you want to make a distinction between compile time versus run time. So when I'm
No,
when
no
I'm
runtime race
compiling,
conditions.
when yeah, I'm about to get you there, but compile time is not the same as runtime. So runtime is when I'm actually executing the contract. Compile time is when I'm producing some interior form and at this and either alongside that or prior to that, I'm checking for properties. So what we're saying is that like today, when you submit a smart contract, it doesn't have any types decorating it. In rolling 1.2, when you submit a smart contract, it will have types decorating it. And so one of the phases of accepting the smart contract is to check that the program has the type that is being asserted. And if it does, then we will add the smart contract definition to the blockchain. And if it does not have the type, we will not add the smart contract definition to the blockchain. Does that make sense?
Yeah, it makes sense, but
So I just
so can you write something like
I'll
this?
get the race
Okay.
condition. I'll get the race condition, but first I want you to understand, that there's two different things, right? There's compile time versus runtime. And
Yeah, I understand that.
okay, all right, cool. So with this, which I gave before, where is it? Oh, it might be on this page. Yeah, here we go. So here, suppose, so this works for all monoids, right? But in particular, so let's remind ourselves what this says. This says that I've got a formula which is going to be which is saying that whatever this is, it cannot be the identity, and it cannot be a decomposition of two things, or a composition of two things which are the identity. Right? So that's clearly primality. And now if I pick as the monoid parallel composition, which is going to be the star operator here, and 0, which is going to be the identity here, this works. This formula also applies to this type system. Now, so this formula says that that processes are single-threaded. So if it's single-threaded, it can't have a race condition. So I'm giving you something stronger right now, and then I'm just approximating what you need to be able to do to prevent race conditions. So this one will give you all the single-threaded processes. So they clearly cannot have race conditions. Now, the one thing you have to worry about is what's this tilde here? And that's why I've been very careful about making sure that we have the ability to interpret things like negation, right? So things like negation are derived in this style. So if you give us an explicit concrete type, then we can take the context with respect to that type and get a notion of negation that way. Right, so that notion will show up as a part of this thing here, right? So when you give us one of these, we can calculate a notion of negation. So this formula will be interpretable. So we can clearly pick out single-threadedness. Now, how do we pick out no race conditions, which is a more general thing than single-threadedness? Well, let's write down some race conditions in the row calculus and see what that gives us. It turns out that there are only two ways to have a race. I don't want to do that. Grab this one. So what does a rolling program that is a race look like? Well, there are only two possibilities. I have for y from x do p in parallel with output q, oops, q on x in parallel with for w from v do r. That's clearly a race, yes? Do you agree?
I don't see the race.
Oh, sorry,
Yeah.
sorry,
I
sorry,
was expect.
sorry. X,
Okay.
Okay. Yeah.
sorry. See the race?
Yeah, that's a race.
Oh, okay. And can you tell me what the other form is?
Uh,
It's 2 sending and 1 listen.
Exactly. Okay, so now that we've classified all races, we're 90% of the way there.
mm,
So how do I write down that something is of this form? Like, we don't really care what's here, so this is going to be a true, right? And we don't really care what's here, so this is going to be a true. We don't care what's here, so this is going to be a true. We only care that this is the same as that and that, right? Okay, so can you write it for me? Tell me what to write. So I'm just going to bold all of this. So now I've got a type, right? And that's going to be true because we don't care what's there. And this is going to be true because we don't care what's there. And this is going to be true because we don't care what's there, right? And in general, we have no constraints. So you'll notice that in this system, I'm not dealing with the lambdas, right? Ultimately I have to deal with the lambdas, but for the time being, I'll just put true here and I'll put true here. So there's no constraints on the variables themselves, right? So now we have, so this is very close, right? That's a little bit weaker than what we'd like, but it will certainly stop all the races. It will stop other things too, but it will stop all the races, right?
yeah, that makes sense. Yeah.
Right? And you can do exactly the same thing for this one. So we have something that's stronger than no races, slightly weaker than no races, catches. And so you can play around with these two to get, oh, and then you have to put a negation on this, right? You have to say not one of these. And similarly for this one. So play around with the two to see if you can tighten it up.
Pratyush, I think you are also asking about the replay of the rolling in when validator receives the and replaying the block from the validator who created the contract, who created the block, and so basically we only need the trace of the races to successfully replay.
Yeah, but
Okay.
no, yeah, but note that's exactly why I was making such fuss about compile time versus runtime. Replay, you're already in runtime, right? You've already done the execution and you're replaying it. And what I'm saying is that that's very different from what's going on at compile time, where we do the type checking.
Can you clarify why you said the first statement was weaker? I was a little confused.
Because this is at the type level, not at the term level, right? At the term level, we need it to be not exactly the same X. And here, what we're just checking is that the X's are the same type. So if it's exactly the same X, it's going to, it will obviously catch the same type, right?
Yeah.
Right? But sometimes it'll be different X's, but in the same type. So how do I, what can I do to be more principled about that?
So no, another aspect is that there can be other things that are happening. For instance, the first part of the for and the second part of the for. The first part of the for, it could so happen that you've written in the code that you're sending it to the other part of the for without changing it. So it's a lot more tricky, because you also need to keep track of what is happening inside the code.
Nope, you don't. That's not true. That's not true. So again, if you go to this level, right? We don't have to look inside P. We only have to worry about the X's. And if you do the other one, it's exactly the same thing. You don't have to worry about the continuations. You only have to worry about the X's.
For instance, in the code you wrote, it could so happen that Q was equal to R. Then it's not actually a race, but it looks like a race.
Oh, it certainly is a race.
Oh, why would you call it a race? Because it's the same thing, right? The execution history is the same, irrespective.
Yes, but you have garbage left over. You still have ones hanging out.
Yeah, but it looks exactly like the other situation.
No. It's non-deterministic. That's the point, right? So if I do this one, right? So, and then but you want this to be a P. No, this absolutely, if this one consumes, this is still hanging around, which means it can interfere with something else.
Okay.
If this one consumes, if this one consumes, this is still hanging around, which means it can interfere with something else.
The reason I will not call it a race is because it's the same continuation, irrespective of which one consumes. The final state is the same.
But the problem is that you still have this one lying around.
Yeah, but that will eat something else, and whatever it eats, it doesn't bother.
But you need, no, that's not the case. It may in fact be deadly to eat the next thing that comes along. So you need, so I count this situation. Now, if you want to say that this is not a race, then you refine your type.
Okay.
Yeah, but for me, I count this as a race.
So the reason I'm not counting it as a race is if there was a parallel X and let's say R, right? This code looks the same. If there was X and Q and there was a parallel X and R, right? It doesn't matter what happens.
I understand, but
Yeah.
that's not the same as
Yeah,
we're talking
okay.
about all programs, not the specific one you had in mind.
Yeah, I understand. Yeah.
All right, it's 8:02. We're way past time. Thank you so much for your time and great questions. I appreciate it.
Thank you.
Thank you. Bye-bye.